Yeah. I was also here. Okay, I was here. Oh, yeah, it's here. Okay. Yeah. Good morning, everybody, and welcome to the second last GR seminar. Today we are delighted to have Aghil, who actually originally started this seminar many years ago, and he's going to talk about this very exciting topic, positive mass theorem about asymptotically locally Euclidean, asymptotically locally flat Toric for manifolds. So Aghil, please take it away.
Thank you so much, Pascal. I'm really grateful to be here. I'm really also happy to be back at CMSA and give a talk about my recent work, which is a joint work with Marcus Khuri and Harry Kunduri. So let's go through our setting. So today I want to discuss about the positive mass theorem in ALE and ALF toric for manifold. So let's define what is ALE. So we will say a complete Riemannian manifold is asymptotically locally Euclidean if outside of the compact set there is a diffeomorphism such that the end is diffeomorphic to Rn minus a ball quotient with gamma. You can put a cone metric, flat cone metric on this Rn minus a ball quotient with gamma, and gamma here is a discrete finite subgroup subgroup of On that acts freely on the sphere. Now, in coordinate chart that you get from this diffeomorphism, you can look at the decay of the metric in this setting. So the pullback of the metric minus this flat cone metric, it actually O2 of the x to this particular power. In addition to this decay for the metric, we impose a scalar curvature integrability condition. And the reason for that is nothing to do with the asymptotically locally Euclidean. It's more to do with the definition of the mass. So you go to the usual asymptotically Euclidean setting when the gamma is a trivial subgroup of On. And in that case, you will have asymptotically Euclidean, which is in the GR setting. We usually call that asymptotically flat. It's a mathematical model for the isolated gravitational system for the initial data set for the isolated gravitational systems. So this is the setting whenever we say ALE, we mean this kind of complete Riemannian manifold. What about ALF or AF Riemannian manifold? So there is no generally accepted definition for ALF. In dimension higher than 5, there are some definitions, but it's not a definition that almost everybody uses and unified. But there is the following definition, which is nice in dimension 4. It's by Ricard, Kadachan, and Lebrun. And this definition is as follows: a complete Riemannian manifold, a 4 manifold, we will say asymptotically locally flat if outside of the compact set you can find a diffeomorphism that the end is diffeomorphic to R plus times sigma, which sigma can be S1 times S2, can be S3, or it can be quotient of these guys. And here we are interested in the orientable manifold also. Now, in addition to that, there is also a triple, eta, t, and gamma on the sigma. Eta is a one form, t is a vector field. Eta t is 1, and interior product of d eta in direction of t is 0. Gamma here is a positive semi-definite symmetric 2 tensor that it's invariant under t, so the derivative of gamma with respect to t vanishes, and the kernel of gamma is the span of t. Furthermore, gamma locally define a positive Gauss curvature 1 on the space of leaves of fluctuation tangent to sigma. So in a coordinate chart, you can write the metric, the pullback of the metric, to be like dr squared. You can look at it like r squared gamma. You can look at gamma like a metric on a sphere, S2, and plus eta squared. Then you have your decay. And decay here is r to the minus half minus k, and we have O2, so the second derivative, up to second derivative, they have stronger decay. We need that for the well-defined definition of mass. Furthermore, we impose the scalar curvature condition, which is the additional condition. The decay here is weaker than the decay that Lebrun they used in their original paper, because they were interested in the Ricci flat, Kähler manifold, I believe. And in that case, you have a stronger decay. Here, we are interested in mass. We can go to the weaker decay. Now, how do you get asymptotically flat? You get asymptotically flat if the manifold is globally, diffeomorphic to the n is globally diffeomorphic to R3 minus a ball times S1. So it's like it's globally diffeomorphic to S1 bundle over R3 minus a ball. So the asymptotically locally flat, you can look at it like locally is diffeomorphic to S1 bundle over R3 minus a ball. So the end is locally like S1 times S2 for asymptotically locally flat. Okay, let's go to the definition of mass. What is the total mass in GR? So in GR, the total mass, if it's defined, it's a non-negative measure that represents deviation from the ground state, assuming a proper energy condition hold. So in the definition, there are one ambiguous object, and that is a ground state. So it would be a non-negative if you know the ground state. So a natural question is, what is the ground state? Is it unique? And does it even exist? And in the case of isolated gravitational system, which is asymptotically Euclidean, the outside of the compact set, the manifold is diffeomorphic to Rm minus a ball. Now it is believed from physical perspective that the ground state is Minkowski space. So if you go to the constant time slices, you get Euclidean space Rn, and you can look at the mass like a kind of a measure for the curvature. So if there is a curvature, when I talk about the curvature, usually it's like a Ricci curvature. If there's a Ricci curvature, then potentially you will have a non-zero mass, because the object will start to bend. The Rn will introduce curvature on your manifold, and the curvature implies the non-negative quantity, which is the mass. Okay, but the condition you need, the proper energy condition for in this setting is really weaker, just the scalar curvature non-negative. Okay, so fortunately we have a universally accepted definition for total energy and momentum for isolated gravitational system, and this is by Hamilton-Jacobi analysis of Arnovit, Deser, and Misner. So it's a classical result. And because we are interested in the Riemannian manifold, we go to the time symmetric case. If you go to time symmetric case of the initial data set for the Einstein equation, the second fundamental form vanishes, and then the initial data set for the isolated gravitational system will be asymptotically Euclidean Riemannian manifold. Okay. In this setting, the energy, the ADM energy, is the same as ADM mass, and you can define it as follows. So it's a flux integral at infinity. Note that here I'm highlighting the delta because this energy is with respect to a reference, and the reference physically is believed to be the Euclidean space. So let's look at each component of this. So E here is the pullback of the G minus delta, and the pullback is through this diffeomorphism of the end. The sigma, in this case, you can look at it like a sphere. So it's like a sphere Sn minus 1. The omega is actually the volume of the sphere in the standard metric. And the nu is the unit normal directions to this sphere. Okay? And you're taking the flux integral at infinity. Now, it has been proved by Bartnik and Kurschel independently that this definition is independent of the diffeomorphism that you take. Okay? So if you look at this definition, if I plug in the Euclidean space, I should get the zero, because I'm computing the mass with respect to my ground state. It's a Euclidean, it's giving me the zero. So a natural question, before that, let me state the proper energy condition. So the proper energy condition in this setting is the scalar curvature non-negative. Also, you can look at it like the scalar curvature bigger than the scalar curvature of the ground state. And what is the scalar curvature of the ground state? It's just, zero. Now, this is the positive mass conjecture. The claim is the total mass that we define of a smooth, complete, asymptotically Euclidean Riemannian manifold is non-negative if the scalar curvature is non-negative. And the rigidity happens if and only if you are in the ground state, which is the Euclidean space. So the rigidity implies a kind of uniqueness for the ground state. That would be the only ground state, and it is the Euclidean space. This conjecture has been proved by the celebrated work of, Schoen-Yau and Witten through a spinorial approach. And there are also some more recent results about the proof of the positive mass theorem, but assuming the dimension is, only 3. So different techniques have been developed during the last 50 years, and there are different proofs of this conjecture in dimension 3. So it's right now a theorem. So you can ask similar question. We can change the asymptote, go to ALE, AF, and ALF, and ask similar question. What is the total mass? So the main kind of physical motivation, the mass would be the deviation from the ground state. It's a non-negative quantity if you fix the ground state and if you find the unique ground state. So I can go to this Hamilton-Jacobi approach, and because the infinity is again flat, so the scalar curvature vanishes at infinity, I can repeat the same kind of argument and come up with the same definition of mass. The only difference would be I have a different ground state. It's not the delta. So the question is, what is this ground state? In each one of these asymptote, give me the ground state and then go to the positive mass conjecture and prove it. Now, there is no conjecture ground state in this setting. So we cannot go to the physical theory and say, okay, this is the ground state and take that. And hopefully in the next couple of slides, I will convince you that's the case. So a natural question is, so what is the positive mass conjecture? If you don't know the ground state, how or why we should expect the mass to be non-negative? The mass is non-negative if you fix the ground state and say everything else has a non-negative with respect to that ground state. If I don't know the ground state, even expectation of positive mass theorem, it doesn't make any sense. So you can have positive mass theorem, but in a very special setting. Either you need to move in that direction or you need to modify or refine the positive mass conjecture. Okay, let's go to ALE. So in ALE, the potential ground state would be just the Euclidean space quotient with gamma. And the gamma here is a cone metric, and since I'm not removing the origin, you don't get a manifold. In the special case, which I am interested in, the Toric case, when you have T2 isometry in dimension 4, the metric can be written like this. So this metric, when you go to r equal to 0, it actually it's a lens space, and infinity is also a lens space, so it's not a manifold at that point. But when you remove the origin, it's a manifold, it's a smooth manifold. It's a Riemann curvature 0 metric, so it's a flat. So it's the best possible case you can get. So if p equals 1 and q equals 0, it will give you the asymptotic Euclidean case. Now, a natural question is, this should be the ground state. These have everything of the ground state. Now, there's a solution which is called Iguchi-Hansen instanton. It's a complete asymptotically Euclidean, Ricci flat. Infinity is the lens space L to 1, and its mass is 0. If I put in that definition, with respect to this ground state, the mass is 0, so there's no deviation from delta. Delta is not a unique ground state. So I found another one, because the mass is 0. Now, there is also a counterexample to this. Lebrun, he constructed a class of Keller manifold by modifying the Iguchi-Hansen solution, and he constructed complete asymptotically, locally Euclidean scalar flat with the infinity, which is LK1, and the mass is negative. So when you compute it with respect to the ground state, you're getting a negative quantity. That guy cannot be the ground state. So this delta is not the ground state. Now, a natural question is, what is the positive mass? If I don't know the ground state, what's the positive mass? So there are some attempts to prove the positive mass theorem. This result is very interesting, and actually it has a lot of information. So this result is by Hein and Lebrun about the Keller manifold. So if you have, Keller manifold, which is a smooth ALE, and let's say n is even, then you can write the mass in terms of a topological invariant plus the integral of the scalar curvature. So let's say the scalar curvature is 0 in a in one particular topology. So that means the mass of any scalar flat in that particular topology is that topological invariant. And that topological invariant related to cohomology group and complex structure under Keller manifold, it can be negative. And the example of that is Lebrun counterexample. So it seems, in addition to the in addition to the infinity, topology play a role. You cannot just say, with respect to any topology, the Euclidean space is the ground state. That's not the case in ALE. There is a result about the positive mass theorem by Dahl. He put a very special condition on the topology. He restricted to he used the Witten-Spinor proof. So we have like a smooth, complete, asymptotically Euclidean spin manifold with non-negative scalar curvature. But he imposed the condition that the end is a spin preserving diffeomorphic to our n minus ball quotient with gamma. So the end is, they have the same spin structure. This is a very strong assumption. And the previous examples, that we have, like LeBron one, doesn't have this condition. And he proved the non-negativity. So this is again some sort of topological condition that you're imposing in addition to the infinity. So you impose the infinity, the decay, and everything else, and the scalar curvature condition, but you impose also topology.
So for the Taylor case,
Yeah.
you could have scalar flat.
Yeah.
That's not even reaching flat. And
Yes.
That would also be ground states, which are not reaching.
Which is not, that will tell us that that guy is not the ground state. Because if any other one, like Bushi-Hansen, can be zero, then, sorry, non-zero or negative, or LeBron example, which is scalar flat. It's not reaching flat.
No. Bushi-Hansen is reaching.
Yeah, but LeBron example is scalar flat.
It's only scalar flat.
It's only a scalar flat. It's not reaching flat. And for that, it's only this topological invariant. So yeah, it's there should be more. I will go to that point. So it took us a long time to understand it. Okay, let's go to AF. So AF, I again go to the special case, and that is like we said is AF whenever it's diffeomorphic to a span bundle over R3 minus a ball. So the end looks like R3 times S1. So I take a flat metric, complete flat metric, like the Riemann curvature vanishes with T2 isometry on this space, and I characterize it with two constants. And the reason for these two constants are more related to the explicit solution. All of them are in this setting. They have T2 isometry. Now here the theta goes from 0 to pi. The phi I has a 2 pi period, and omega here characterize the direction that the Killing vector field has a bounded length. If L omega is rational, then it has closed orbit. And what is L? You can look at the L when omega is equal to 0. You can look at the L like related to the circumference of this S1. At infinity, with 2 pi L. Or in general, you can look at it like it's related to the area of the flat torus. Okay. Clearly, when I go to the origin, when omega is non-zero, I will get orbifold. If omega is equal to 0, then I will get, a manifold with this metric. It's nice. Everything is nice. Is this the ground state? So unfortunately not. So Riemann-Nordstrom, it's a 2-parameter family. It's complete. Is asymptotically flat. Is a scalar flat. Topologies are 2 times this 2. Infinity is the same as this guy. Is this 1 times this 2. Omega is 0. L is that positive quantity. And the mass is ml. L is positive, but m can be anything. It's completely free here. It's not like the case of the Riemann-Nordstrom spacetime that the m should be always bigger than or equal to q. M here is a free parameter, so it can be negative. And whenever it's negative, it will tell us the deviation from that guy is negative. That guy is not the ground state. So this flat, nice metric is not the ground state. Okay? Now, is there a positive mass theorem in this setting? Let's focus in dimension 4. And there is a generalization of the Dahl result by Minerva to this AF manifold. So he focused on the 4 high dimensional, but let's focus on the 4-dimensional. 4-dimensional complete AF spin manifold with non-negative scalar curvature. And the end is again spin preserving diffeomorphic to R3 minus a ball times this one. And then the mass would be non-negative. So you put a topological condition, but the problem with this topological condition is most of the explicit solution, you just rule out those explicit solutions. You cannot say anything about those explicit solutions, including the Riemann-Nordstrom instanton or Schwarzschild instanton. There is a more recent result by Chen, Liu, Shi, and Zhou. they have a different approach, and their approach is like a generalization of Schoen and Yau approach, but for the case of dimension 3 to 7. And in dimension 4, you have a complete asymptotically flat manifold with non-negative scalar curvature. Then the induced map from the embedding of the end to the manifold will give you a map from the pi1 of the end to the pi1 of the manifold. And this map must be injected. So again, a topological condition. And or non-zero, then you get the non-negative. You see, the problem of this is the end is not simply connected. So pi1 is non-trivial. That implies the pi1 of the manifold should be non-trivial. So that implies the manifold should not be simply connected. Most of the solution, 90% of the known solution, they are simply connected. So you cannot apply this theorem to any of those explicit examples. Okay? So that's the problem with these two results. They put a topology condition, and I think the belief is I want to prove positive mass theorem because there is a positive mass theorem in asymptotic Euclidean. So let's put a topology condition and go to that kind of restricted topology and prove it. So all of these explicit solutions are highlighted here. They are simply connected and they do not satisfy the topological condition in this theorem. Now what about ALF? So ALF, there is no flat metric, so I don't have the luxury of Purvis cases. We could not find a flat, asymptotically, locally flat, metric on R4 quotient with, let's say, ZP. I'm in the T2 symmetry, so I'm taking my space to be, ZP. You come to ZP. Now there is a Ricci flat one. There is a Ricci flat instanton. It's called top knot instanton. When you slightly modify that top knot, the top knot at infinity is it's like R4, at infinity is the street, but you can actually go to this metric, which is very similar to top knot. It comes from multiple top knot. It's a metric which is Ricci flat. It has orbifold singularity at origin, and it has conical singularity in one part of the axis of the rotation. The period of theta is 0 to pi, and the pi are 2 pi, and h is this fixed one. So this is Ricci flat. This is the nicest thing we could find with the simplest possible topology we could find. Now you can get a manifold outside of the ball if you put q equal 1. Then the infinity would be LP1. So you get a smooth manifold on R4 minus, you can say, the origin, quotient with ZP, and it's Ricci flat, it's nice, and it doesn't have conical singularity. Now, is this the ground state? That's the best I can find. It's Ricci flat. There is a charge top bolt instanton. It's a 2-parameter family of top bolt. It's a scalar flat. It's asymptotically locally flat. So in the case that P and Q equal to 1, let's put in B, P and Q equal to 1. The infinity would be a sphere. Then this guy has the same infinity. If you compute the mass with respect to this guy, which is Ricci flat, it's again negative. So this guy cannot be again the ground state. So we have a fundamental problem, and that is we don't know the ground state. So why should we even expect the mass to be non-negative? I need to first find the ground state. Now you may ask, okay, what is so special about AE? So this is so special about AE. There's a proof of the positive mass theorem, by Lee. I think this is a well-known fact, but Lee actually has this detail in his paper using the Ricci flow. So he used the Bishop-Gromov volume comparison theorem, and he combined it with a kind of uniform estimate of the metric, and he showed whenever you're Ricci flat in AE, you're just flat. You're just Euclidean space. There's no other Ricci flat. So that's deep. That's very, very strong condition. That's tied to the positive mass theorem. It seems mass only detecting the Ricci flat and not the flat. So if you go to the ALE, different Ricci flat, different lower bound for the mass. That's a kind of intuition we can get from this argument. If you go to AF or ALF, different topology, like different infinity structure, you have a T2 metric, toric metric, so infinity characterized with this L and omega. So if you fix those, you have different Ricci flat, different lower bound for mass. So everything leads us to this conjecture. like you should refine the positive mass conjecture. And what's the refined version is the following. So take a complete asymptotically Euclidean or locally Euclidean flat or locally flat Riemannian manifold with non-negative scalar curvature. The minimizer of the total mass is actually Ricci flat Riemannian manifold with the same topological, geometric, and infinity structure. Now, you may ask, okay, what are these topological, geometric, and infinity structure? This is part of the problem. This is part of the conjecture that you need to figure it out, okay?
In the Kähler setting, it also depends on the Kähler class, right?
Yes.
The topological.
Yes, which is a topological condition. So it depends on the topology, geometry, and infinity. The mass only detects Ricci flat. The mass doesn't detect flat. In the AE case, flat is Ricci flat is flat. So you have this luxury that we get the one minimizer and one unique ground state. In particular, this state that in every topology or geometry or infinity structure, there is a ground state. If there's a Ricci flat, a smooth Ricci flat, that would be a ground state, which we will refine even this conjecture. We prove something a little bit more strong in a special Toric case. So what about the rigidity? It's for that Ricci flat one. So there are more than one ground state. This is a mass. It's better to call, so we have a dilemma. What do you call this? It's a mass comparison. You're proving the mass is bigger than the mass of Ricci flat. Now, what about respect to? You can fix the infinity and compute everything with respect to a fixed guy. And then you can compare them. Now, a natural question related to this is there a unique smooth Ricci flat metric? With the E within each possible topology. So can I go to each possible topology, find a smooth Ricci flat one? So this was like, we go through the literature, there's a brief kind of, some of these results, this is definitely not a comprehensive one. I just tried to list some of them. What the uniqueness and existence. So there is a classical result by Kronheimer. If you have a smooth hyperkähler Ricci flat ALE, then they are classified for man. You know what they are, okay? There's more recent result by Acksteiner, Anderson, Dolph, Nilsson, and Simon, which says if you have a four-dimensional smooth Ricci flat ALF manifold with the infinity LK1 and the U1 isometry, then if you fix the topology to be S4 minus S1, then it's Kerr, instant on. If you fix the topology to be CP2 minus a point, then it's Taub-Bolt. If you fix the topology to be CP2 minus S1, then it would be Hermitian or conformally Kähler. Now, what do we know about this Hermitian? There's very recent result by Lee. It says any Hermitian Ricci flat, which is non-Kähler, asymptotically locally flat for manifold must be Toric. So it has T2 isometry. So any Hermitian one is a limited case of the Toric one, but any Hermitian one, which is Ricci flat, is Toric. And there's a classification of these, Hermitian guys. It's like this result by Picard and Godachan, which is before this, the Lee result, is a smooth Ricci flat Hermitian Toric non-Kähler ALF for manifold is either Kerr, Gentile, Taub-Knot, or Taub-Bolt instead. So there are not I cannot go to different topology and find many different smooth ones. But something can save us, and this is this result. So this is the result using the harmonic map. So by Kunduri and Leschetti. So the result is using the harmonic map and existence of uniqueness and existence solution. So they prove that there exists a unique Toric Ricci flat. So here we don't have a complex structure. Everything is Riemannian. There exists a unique Toric Ricci flat AF Riemannian four manifold in each orbit space, which is the quotient of the manifold with respect to the T2, and infinity structure. So if you fix the infinity structure, the L and W that I mentioned, and you fix the topology, all of the Toric possible topology, you can find one solution, which is Ricci flat. Unfortunately, that solution usually has conical singularity, so it's not smooth. Okay? And this result is actually generalized to ALE and ALF case by Kunduri, Khuri, Kunduri, and Relativity. It's a work in preparation, so they will submit it soon. Now we go to our result, and we see that so all of these Hermitian are toric. We have existence of Ricci flat toric.
You expect these formation manifolds, like these Kerr and so on, they're ground states
They are ground state in the topology. Yes.
in their topology.
Yes.
But I thought like usually the Schrock shield is not the ground state.
I will show you. Give me a little bit, a couple more slides. I will show you how you need to reformulate that. So for complete toric form manifold, for the compact case, there's a classification, classical result by Riemann and Ehrlich, which classify these complete compact form manifold. This classified result has been generalized to non-compact setting by Holland and Diaz-Diabit. So in particular, you can highlight our setting like this. You take a complete, simply connected, non-compact toric. Toric means you have effective T2 isometry. It has a fixed point, and you do not have discrete stabilizer subgroup. You take this Riemannian manifold, then you go to the orbit space. It would be simply connected. It would be homomorphic to upper half plane. So I know the orbital space is just fixed. The fixed point of your isometry are corners will show up in the orbit space. So at the boundary of the orbit space, you have a finite number of corners, which we denote that by AI. And the boundary of this upper half plane, you can decompose it to a smaller interval, two semi-infinite interval, and a bunch of finite interval. And if you fix these intervals, you get the fixed topology. And what are the all possible topology? You can get many different topology, like CP2, L copy of CP2, connected sum with L copy of CP2 conjugate, connected sum with S2 times S2, and minus a ball or minus a swan, something like that. So from now on, we call these intervals rods. What will happen in non-simply connected setting, like the result of sheet? So if there is no fixed point for T2 action, and I want to have a simply connected orbit space. So if you have a simply connected orbit space, then the topology will be fixed. It's just S1 times R3. Okay? So the orbit space would be our half plane. There is no fixed point. There's only one infinite rod. So this is the orbit space. That's the way you should look at the orbit space. The rho direction is the one which goes from 0 to, let's say, infinity, and the z direction goes from minus infinity to plus infinity. Now, each rod, the way you topologically characterize that is through the associated rod vector. What is that rod vector? Is actually, it will give you which Killing vector field, which combination of Killing vector field vanishes on that, stabilizer, subgroup. Now, here the x1 and x2 are generators of the T2 isometry. So from now on, whenever we have a collection of the rods with their direction vector or rod vector, we call that rod structure. So rod structure will give you the topology, which topology you are. Now, you can get a manifold, a rule out orbifold singularity by adding admissibility condition. And that means the determinant of the matrix, which coming from the columns are, rod vectors of adjacent rod, must be either +1 or -1. So in that case, you do not have orbifold singularity. In our theorem, we allow to have orbifold singularity. So we try to weaken this condition. Now, in our theorem, we have a terminology which is same orbit space. And whenever we say two manifold has the same orbit space, they have the same topology, they have the same rod structure. But furthermore, we impose one geometric condition. They have the same rod length. So even you fix the rod length. For semi-infinite one, so there's no way to fix it. But for the finite one, when you fix it, the semi-infinite one will be fixed because they have infinite length. Now, what about the coordinate? So there is a coordinate system on this class of manifold. And the metric in this coordinate takes the following form. It can be expressed in this form. So you have e to the 2 alpha d rho square plus dz square, gij, and then you have e phi square plus ai, a dxa. So here xa are rho and z coordinate, your coordinate on the orbit space. Phi, we always fix the period to be 2 pi. Okay, and the rho goes from 0 to infinity. And all of these functions are function of an orbital space, so a function of rho and z. Now, this coordinate system exists. In dimension 3 has been resolved. This is a result of push-up. And in high dimensions, this is a work in progress that is showing the existence of this coordinate. Now, how do you go to the usual polar coordinate at infinity? We put two different conditions. In the case of ALE, we put the following transformation. And in the case of ALF and AF, we put the following, red one transformation. Okay. Now, how do you detect the conical singularity? So conical singularity is actually angle deficit on the axis rod. And the way you find it is through this following formula. If the cone angle is equal to 0, then that Killing vector field which vanishes has a pair 2 pi. Okay. So this is our theorem that we prove. So take a complete any of these asymptotes, AE, ALE, AF, ALF, toric Riemannian 4 manifold with non-negative scalar curvature. Let's say the cone angle on the rod II is just theta I. Okay? Assume the M0 and G0 is a Ricci flat toric 4 manifold with the same orbital space and same infinity structure. And call the cone angle of that to be theta I of 0. Then we prove the mass of the manifold, the data, is minus the mass of the Ricci flat one is always bigger than this cone angle. Okay? And you can get the rigidity or equality here if and only if the manifold is isometric to this Ricci flat. To prove this, we put additional condition. So the cone angle can be a function of z, and we assume that on semi-infinite rod, they are finite. Otherwise, this integral that we have will blow up. Okay? They are integrable. You can say that.
So this applies to these like Euclidean short shield.
Everyone can be included. Everything.
But your perturbation is also toric.
Everything is toric. Yeah. Yeah. So every known one that you know, you can put in inside this one because all of them are toric, as far as I know. Now, in this theorem, manifold can have conical singularity, as you can see the cone angle. They can have also orbifold singularity at corner as a fixed point. We did not fix that to prove this theorem. Now, if you have a smooth case, no conical singularity, then we prove the conjecture. As you can see, the conjecture is mass is bigger than the mass of the Ricci flat. And rigidity happened for the Ricci flat. But toric, we have a toric assumption. So in general, you can even refine the conjecture more. You can say the minimizer of the mass plus the conical one is the Ricci flat. You can rewrite our inequality like this. So there's a mass term, there's a conical part, and then you get this inequality.
So is the extra excess term related to the scalar curvature?
The extra one? Everything is related to scalar curvature. Everything comes from a scalar curvature. It's the boundary term of the scalar curvature on the axis rod. The cone angle. If it's a smooth, there's no cone angle. So those guys will go away. If it's not a smooth, then okay, you have conical singularity.
So these are just the cone angles.
These are just the cone angle.
But you could have like positive scalar curvature in the
You
interior.
can have positive scalar curvature.
It
Yeah.
doesn't measure that. It doesn't see that.
What do you mean? It doesn't see? It does see that. It says mass of that guy, which has positive scalar curvature, is bigger than the Ricci flat. With the same topology.
Right, but like you can locally, I think for these metrics, you can locally perturb the scalar curvature up so that it's non-zero in the interior and still.
It's fine. It will still, as long as you boost it up in the positive sense,
Yeah.
then it's fine. You can put it over
But you
there.
don't change the mass when you do that. Or
So you change the whole inequality. Look, there's a cone angle here. So you're telling me the cone angle will present, so the scalar curvature will change. The manifold, you change it. You're perturbing the metric.
but only on a compact set you can push it up.
Yes, but that shows up somewhere in the theorem. The mass is at infinity, but also all the topological structure or the cone angle will also show up. So when you tell me like you take the Ricci flat one and
But
boost it?
just take the smooth one, no cone angle. Like take the curve.
Okay, yeah, curve.
And then you just push it up in some compact.
Yeah, so the mass of that dot, which you push it up, is bigger than the mass of curve.
But at infinity it's the same, so it should be the same. Isn't the mass only measured some integral at infinity?
So you cannot do that. Our theorem implies that you cannot do that.
You cannot do that preserving the toric, but I think you can do it without preserving.
Yeah. So you're going to a setting which is different from our setting.
Toric condition is vital.
We are using everything is toric. It's like you're in that kind of setting. And all of the well-known solutions are toric. So, but I understand you want to say, okay, I can do this too, but you will be outside of the assumptions of our theory.
Okay, can you go back one slide?
Yeah, sure.
Like before that.
Before that?
Yeah, this coordinates. So if I just write down the Ricci flatness for the metric J, what are the equations I would get for the connection?
Harmonic map. You get if you part Ricci flat one, this implies a harmonic map for the G.
And what about the connection?
Connection you can for the Ricci flat one, the connection is 0. You prove the connection is 0. So AI are just going. The Ricci flat they don't either. Okay, so now this is a refinement. So if you go even to Schoen-Yau result or Witten result in the measure 4, they prove the mass is bigger than flat. Now we are allowing even you have a metric with conical singularity. For those cases, in each topology you have different minimizer. Okay? So even in AE, this is new. So now we go back to your question. How can I discuss this with the Schwarzschild? Schwarzschild and Reiser-Nordstrom, they have same topology, same orbit space. But Reiser-Nordstrom has negative mass. I'm claiming the Schwarzschild is the minimizer. Schwarzschild has positive mass. So let's discuss that. So let's go to this setting. So if I take Reiser-Nordstrom in instanton and Ricci flat Schwarzschild in instanton, both of them are smooth. They have the same topology, but there is a problem. The problem is they do not have the same finite rod or the same infinity. I need to fix that. So there's a trade-off. I start to fix one of these conditions. Let's fix the finite rod. Then I will be outside of this smooth. Because when you fix the infinity structure, to make it smooth, you need to fix the infinity structure. For example, you need to change the period of that dt to be like 8 pi m, something like that. And we are only having a 2 pi period, and we want to have free, the infinity. So you fix we leave the infinity to be free, but we fix the finite rod to have the same length. Now both of them has conical singularity. That would be the trade-off. Okay. Now, but still you can apply our theorem. There's no issue. So you take the Reiser-Nordstrom and Schwarzschild instanton. You take these rod points, like both of them are L square root of m squared plus q squared. For these cases, the mass of the Reiser-Nordstrom is just ml2 over 2, and the mass of the Schwarzschild is positive. It's just square root of m squared plus q squared. It's just that rod point. Now let's go to our theorem. Our theorem is the following: the mass of the Reiser-Nordstrom minus the mass of the Schwarzschild plus the extra integral, which is a conical one, should be non-negative. And that's the question: is it non-negative? If it's non-negative, then okay, you have the Schwarzschild minimizer in the sense of when you include the cone angle too. So let's pick x to be this log term. Then you can rewrite that expression in this form. Note that when q is equal to 0, x is equal to 0. And then in that case, this quantity is just 0. And when you differentiate this quantity with respect to x, forget about the coefficient, just the inside the bracket. That's an increasing function. So it's not negative. And the rigidity happen only when q is equal to 0. So Ricci flat Schwarzschild is the minimizer. You just need to go to the setting of the theorem. And when you compare it with Reiser-Nordstrom, Ricci flat Schwarzschild is the minimizer.
Okay, so you in the middle you write the mass of Schwarzschild m squared plus q squared. Is that because you fix the Rod length, like. Same because the Q is coming because of that.
The mass of the short shell, yeah, fix the rod length. The mass of the short shell would be L over 2 times the rod length.
Yeah.
Rod points, which that is usually in short shell is m. Here is like a square root of m squared plus q squared. So is that point. So a sketch of proof. Let me give you a sketch of proof of 10 minutes. Okay, so first we add the auxiliary coordinate. Let's call that phi. And the Euclidean metric on R3 can be written in d rho squared plus dz squared plus rho squared dv squared. So this is like I take the orbital space, I add the auxiliary coordinate, I get R3. Now I define a function and a matrix. The function z would be, you can look at it like deviation from Ricci flat. So Ricci flat one, the determinant of g has rho squared, but for the other one is not. So you can look at the z like that. And what is phi? Phi is like when you renormalize g such that it has to be determinant 1. Okay? Now, if you look at the scalar curvature, it looks like this. And f is, as you said, is related to the connection. Now, since the determinant of phi is 1, phi is a symmetric matrix with 3 functions that we need to find. Since the determinant is 1, we only have 2 free functions. I define these 2 free functions in terms of the Dij component. Now the metric looks like this. Now what's the problem? The problem is this V and W blew up. And they blew up in completely different ways in different rod length. So, so we need to do something for that. So we define these Green functions. So Green functions on the interval, the Green functions that blew up on the interval a to infinity is the first Green function. The second one give you the blew up at minus infinity to b, and the third one is to give you the blew up on the finite interval. Now, it took us a long time to come up with these Green functions because you want to renormalize the singularity, and you need to first figure out how are the singularity of v and w on different types of rod, and how to remove it. So now I define a new function in terms of these Green functions. It is still a Green function. It's a linear combination of this. And this Green function blew up everywhere. But in some interval, everywhere on the axis. But on some interval, it blew up like log of rho. In some interval, blew up like minus log of rho. Okay? And that depends on topology. How you can characterize the topology here, there's a constant SI. SI is equal to 1 when the rod vector is 1 and 0. And when the CI2 is non-zero, then the SI is just negative. Now we renormalize V and W like that, like we add and subtract to this gradient of V and gradient of W. And we repeat the same thing for the Ricci flat one. Clearly you will have a new V naught, new W naught. Now, you subtract them. Scalar curvature of the Ricci flat, which is 0, but you take that extra term and subtract it from the scalar curvature of the original data. You integrate by part all the divergence. You will get one boundary at rod, like a ball about the rod. One boundary is cylinder above the axis. One boundary is sphere at infinity. One boundary, one bulk, which is we call that reduced harmonic energy. And what is that? It looks like this. It looks like the difference of these two. And this is finite. The left-hand side you can show using the decay, using the asymptotic condition. The left-hand side is finite. The right-hand side must be finite. But note that each one of these kind of positive term and negative term, one coming from the mg and another one coming from the m naught and g naught, are actually blew up individually. Now we prove this following gap estimate. So let's take this side to be V and W. Is smooth at except at axis and corners. Then you can find for all of the possible asymptotes, ALE, AE, ALF, AF, you can prove that actually the reduced energy has the following lower bound in terms of the distance between psi and psi naught. And what is psi naught? It's coming from V naught and W naught from the Ricci flat. Now let's go to the proof. Sketch of the proof of this one. You go to the hyperbolic space and you can write the metric in the hyperbolic space in terms of V and W like that. Now, the harmonic energy of a map from R3 to this hyperbolic space over a finite domain omega can be written in this way. If you find the critical points of this energy, would actually be exactly, can show it's exactly the Ricci-Flat data. So it's just V naught and W naught. So it's a critical of the same thing with the same orbit space here imposed. Now take a geodesic deformations from the solution psi naught to the solution psi. Now, if you use this, if you use the fact that this psi t is a geodesic, and use the fact that H2 is negatively curved, you can compute the second variations of the harmonic energy, and that would be bigger than this distance function, the gradient of the distance function. Note that here I'm not including the axis. And if you integrate twice and use the fact that psi naught is a critical point, then you prove the gap estimate. But note that this gap estimate is not everywhere. It's not on R3 because E blew up. E is actually infinity. It's E blew up on the axis. So the question is, I know what this happened for E, but what is the relation between E and my reduced energy? So this is the relation between E and reduced energy. So you can write E in terms of reduced energy plus the E of the Ricci-Flat one and plus some boundary term. Now, I want to use the convexity of E and prove a convexity for I, or the reduced energy, and I want to avoid these boundary term and that bulk term or the energy of the Ricci-Flat one. The way I do that, I apply a cut and paste argument, which is like started with the the work of Zhou and Schoen to prove the mass angular momentum inequality. So I cut and paste this, but in a very completely different way from the way they did it, because here is you have a very sophisticated topology. And I use the convexity of E on this region like omega away from the axis and infinity. Now, what is our cut and paste is the following. Take this is just, let's say this is like a three-dimensional, and that's your z-axis. Go to take a delta bigger than 0. So cut and paste psi to psi naught outside of a ball with a radius 2 over delta. Then you can show the reduced energy of this cut and paste data. It actually goes to the reduced energy of psi. Now, the difference between our approach and the Zhou and Schoen is the following. So in each rod, over there you had only one rod. Here you have different rods. And in each rod, there are different blow up for V and W. Sometimes W is finite, V blew up, sometimes it's vice versa. So you need to glue it differently in different region. So here you can see the blue region and the pink one. So we cut and paste psi to psi naught, but sometimes we only cut and paste like V, sometimes we only cut and paste W. But also we show that the reduced energy as epsilon goes to 0 of this cut and paste data goes to the reduced energy of psi. Now to make it a smooth, you need to treat this discontinuity or these disks, which here in this picture are just a line. Each line is a disk, and this is like a cylinder about the axis. So for that, you take a ball about that corners, and you cut and paste with the new parameter delta bar, and you cut and paste with the original like Ricci-Flat one, psi naught. Now, for delta bar positive, strictly less than epsilon, strictly less than delta, strictly less than 1, you get this cut and paste data, which is a smooth everywhere. And when you take the limit with the following order, it converges to the reduced energy of psi. Now this is nice because very close to the axis, you either cut and paste one part of the data, the other part would be linear. You can show the geodesic, which connecting these two data, is actually linear. So all of those boundary terms, when you're differentiating twice, will go away because the geodesic is a linear map. And the bulk term clearly go away because it only depends on psi naught. And you can get the following, estimate for the reduced energy. Now, if you use the fact that psi naught is a critical point of reduced energy as well, and use the Euler-Lagrange equation, you can show that the first variation vanishes. So you integrate it twice and integrate it another times, and then use the Sobolev inequality to get the gap estimate. So in particular, we prove this. We prove this, all of these boundary terms are bigger than this distance point. And then what will happen about the boundary? Boundary at infinity, you can show it's a difference of masses. Boundary at axis, you can show it actually goes to the conical part. And boundary at corners, you can show it's equal to 0. And that's it. That implies the inequality. What about the equality? When you go to the equality, then the distance function will give you the harmonic map are the same. And from there, you can construct alpha from the scalar curvature equation. So they will get the same harmonic map, and then because the left hand side would be 0, so the right hand side is 0, the distance is equal to 0. So as a result, you will get the same harmonic map, the same alpha, and AI you can prove is equal to 0, so same metric. You're done. Thank you for listening.
Thanks, Aghil, for the wonderful job. Do we have any questions from the audience?
So the bulk term, the harmonic map, like term, is it what is the bulk term again? The harmonic map energy.
The bulk term, you can look at it like the difference of the.
So you look at a harmonic map from M to M naught.
No. It's a map from R3 to H2. Nothing to do with M and M naught. Each of those coordinate over there in harmonic map, the data like psi, E, and W will give you the metric in the target, right? So it's a map from R3 to H2. Now the reason we want that R3 because we can prove the existence. The reason we want the simple current is we can prove the existence of the coordinate, and from there you can get this nice structure.
So somehow this is like a toric result, really.
This is a toric result.
Like without the toric, this should not be true.
So without the toric, let's go. So yes, the question is, what is the ground state in that case? It's really, you should be able to construct a Ricci flat one. In the toric one, you can still in each topology.
I think only the hyperkähler ones are like true ground states, because these Hermitian ones, there's this result saying you can perturb the scalar curvature up on the compact set. Well, like.
So how do you, okay, so that's the thing, like that's my thing. How do you see the ground state and what are the mass of these? So something which is still is a question for me is like, what about these Ricci flat? Can you prove the mass of all Ricci flat are positive? Like up to here, you're proving a comparison.
But no, right? I thought the ALU ones are not positive. They have a negative mass, the Ricci flat ones.
Yeah, so that's a tricky one. When you get negative mass, there's a different way to interpret this. In the case of the negative mass, you can prove, potentially, there is no smooth Ricci flat. When somebody find a negative mass, that's my conjecture. Maybe wrong.
No, but ALE, like these ALE spaces, they have negative mass. This Kronemer spaces.
Yes.
In this Hein.
So when you say negative mass, so first of all, what kind of mass they are using and with respect to what they are using?
The topological term in this.
They use the usual ADM.
Can be negative. That lower bound is negative.
For all of those Ricci flat ones?
Not all of them, but it can be negative.
Oh, interesting.
Yes.
But it does depends on even complex structure, isn't it?
It does depend.
So it's some sort of
But whenever then there is a.
So if I change the complex structure, does the mass change?
It should, yeah. I think so. It would depend on the complex structure and the Kähler class.
Yes.
Yeah.
So if I change that, then the mass is changing. So
right.
It's like you putting an additional condition on the Riemannian manifold.
But somehow, like my sort of intuition is that only the hyperkähler ones satisfy a positive mass theorem. These are the ones where you cannot even locally perturb the scalar curvature up in a compact set, because there's a paper of Dahl and some other person where it says for these Hermitian like Euclidean short shell, Euclidean curve, Chen tail, you can do this Corvino-Schoen construction where you just locally perturb the scalar curvature up in a compact sense. So it would become
But it's
positive.
still the mass
But
specific.
the infinity is still isometric to
So
Schrödinger.
that's that.
This is
You see, that would be really good for us because this would be the only class that you can prove.
yeah. I think this is somehow like you need additional assumptions like the toric to get this result for these permission.
The toric one, there are several tools, and the main one is this harmonic map. So you can
Right.
prove the existence of all of these Ricci platforms, even though they're not as smooth. But it doesn't matter how complicated you make the topology, you can still. But that's interesting. Is that the new result? No.
It's dull in some other. I can send it to you. I don't know. Maybe it's been like 5-6 years. Yeah. But so like I think that the hyperkähler ones are rigid. Those ones are locally rigid, and that you cannot do this. Like, so somehow they do this Corvino-Schoen thing, but up to second order. Like somehow like it's rigid up to first order, but the second.
So
order
on a compact region, you can modify it, but globally the mass doesn't change it.
Yeah. In fact, it's isometric in infinity. It's completely
I
it's
see.
isometric in
Gluing of
infinity.
curvature.
It's a gluing is
Corvino-Schoen.
yeah type thing. But
It's interesting.
to all of these Hermitian ones you can do that, but the hyperkähler ones are rigid. So the hyperkähler ones locally you cannot compactly perturb the one. So I think only the hyperkähler one should be the grounds.
I see.
The non-hyperkähler ones are somehow unstable. If you allow like.
But how you can actually prove that when you are only in the Riemannian setting is what I'm saying. You don't have this kind of Kähler structure or hyperkähler structure.
But you can prove just using the existence of spinners, I think, that you cannot locally perturb the scalar curvature up in a compact set.
But the way you're saying is like only in that Krotheimer topology you can have a positive mass theorem.
It's local, it's not a global result. So like somehow there may be something far away that has.
Yeah.
But locally at least, you can prove, I think, using spinners that you just cannot perturb the scalar curvature up on a compact set while preserving the
Yeah.
So local is in a modular special matrix.
Yeah, basically, yeah, like a.
Yeah. I see what you're saying. Yeah. It's interesting.
Yeah, I think it's quite interesting.
Okay, how do you show that this connections go to zero? Because I'm kind of interested in it's like
So you need to
it
go.
seems like a Maxwell kind of term.
Yeah. You need to go to the harmonic. You need to go to the Ricci curvature.
Yeah.
So when you put the Ricci curvature equations, when it's simply connected, you can actually use the Frobenius theorem.
Right.
And then a nice kind of reference for that, you can go to the Harmonic. There's a static, what is it called? Domain of structure, something. There's a paper with Harmonic. So when you impose the Ricci flat one, it's a Riemannian case, then you have the harmonic map plus you have equation for A. You can show those at all of them matches for the case of the Ricci flat. Yeah. So it's from the Ricci equation and the Frobenius theorem.
Yeah, that's interesting.
That's quite interesting.
You know, like these kind of theorems for like, is it more difficult or like, or are they already exist for like an asymptotically locally hyperbolic cases?
The hyperbolic case?
Locally hyperbolic.
So the problem is the harmonic map. There's no harmonic map when you go to that kind of asymptote. There is no harmonic map, there's no coordinate system like the ones that you can prove. So it's like, this goes back to the same story of the uniqueness of Kerr-Dessiter. So there's no kind of uniqueness result in that direction. You cannot prove when you look at the Ricci flat equation, you get a bunch of equations. One of that equation will give you a harmonic function, which is rho, and then you can go to the conjugate of that harmonic function. I'm talking about let's talk about the space-time version.
Sure.
The conjugate of that would be the z, and then you get this rho and z coordinate. You cannot do that whenever there's a negative, when the non-zero cosmologic constant. We tried, we couldn't, and in the literature I couldn't find it. So there's no such a coordinate, and as a result, they cannot go to the harmonic map. So the basic would be complicated. You see what I'm saying?
Yeah. So this technology kind of fails.
Yeah, technology failed. You need to develop a new one. And potentially over there are so many exotic cases that will avoid this kind of. So positive mass theorem, it's very tricky. In the hyperbolic case, there are some results. In the global, there's one, I think it's Spinel one.
Did you understand that?
think include Anderson, maybe crucial.
Crucial too.
Yeah. There's no, but for the toric, like the one recently we did with Marcus Khuri and Pekan, the infinity is like torus.
Well,
So
we do
it's-
have one article. Yeah.
But then if you go to the other the infinity with different genus, like
Yeah.
a higher genus, then
Yeah.
there's no positive mass. I don't know. The
Oh, there is no point in master.
as far as I know, the
Oh.
mass can be negative. It's like the result of Dan Lee and Neves that they prove Penrose inequality, but the mass aspect can be negative. So in the hyperbolic case, everything is more exotic and complicated. It's like here, ALE, ALF. In AE, everything is very rigid and nice.
Any more questions from the audience? Yeah.
Okay.
Can we? Okay, then we can stop the recording, I guess.